In this video, we're going to be discussing some of the details of the chi-squared analyses, focusing on some of the general setup necessary to implement both the chi-squared goodness of fit test and the chi-squared test of independence. So recall that there are two chi-squared tests, the goodness of fit, which compares a single categorical variable to pre-specified counts or percentages. And again, if it's percentages, we'll use those percentages and turn them into counts for the comparison. We also had the test of independence, which compares two different categorical variables or more and determine if they are independent of one another. Both of these used the observed counts, which are what we see in the data, as well as what we're going to call expected counts, which come from the null hypotheses. So these terms of observed and expected are going to be terms that we're going to continue to see. And when you hear me say observed, think about the counts that we had in the data when we made our contingency table with the data. And when you hear me say expected, think the counts from the null hypotheses, either based on the counts percentages in the goodness of fit or based on the assumption of independence, where we calculate what the expected counts would be if they actually were completely independent in the test of independence. Now, I find this kind of fascinating because often you'll hear these described as two tests, and in a way they are, but both the chi-squared goodness of fit test and the chi-squared test of independence use the same test statistic and the same critical value distribution, which I find kind of interesting. And ultimately, the reason for this is you're really running the same test. The goodness of fit versus test of independence is less describing differences in the test and more describing differences in the context of when you do it. You do goodness of fit if you have a pre-specified distribution that you want to see if that fits the data, goodness of fit. You do a test of independence when you have multiple variables and want to see if they're independent of one another, test of independence. So both of these are going to use the same test statistic and critical value because both of these are the chi-squared test. So the chi-squared test statistic is given in this equation, that the test statistic is equal to the sum over all of the rows and all of the columns of the observation in a particular cell minus the expected value in a particular cell squared divided by the expected value in the particular cell. So here, when you see ij, really remember that ij, is related to the location of the cell. So recall in the previous lecture video, we did O sub 2, 1 to represent row 2, column 1. So this is just saying add up for all the rows and all the columns the value in each cell. So if you think about our matrix, one entry in the matrix we'll call a cell. So the value in each cell minus what we expected to be there squared divided by the expected. And again, depending on the test, we'll have a different way that we calculate the expected, but we're going to talk about that in a second. So we're going to have this formula for calculating this in a second. Observed is just what we observed. And really, you take observed minus expected squared divided by expected and add all those up. And that's it. That's your test statistic. So it's pretty straightforward. Again, O, the observed count in that particular cell, the cell of the ith row in the jth column. E is the expected count. Excuse me, this is a typo. This should say expected count in row I, column J. Excuse me. So fix that in your notes, please. And distributed as a chi-squared with degrees of freedom of I minus 1 and J minus 1, where I and J, capital I and capital J, are the total number of rows and columns. So I is like the generic placeholder, lowercase I, and lowercase for the row. Lowercase j is kind of the generic placeholder for the column. And this summation notation is saying add up over all of those values. that could go into these placeholders. The capital I and capital J is asking how many rows and how many columns. So capital I is how many rows did you have? Capital J is how many columns did you have? And so for the chi-squared with the degrees of freedom, we will take the number of rows you had, minus 1, the number of columns you had, minus 1, and multiply those two numbers together, and that gives us our degrees of freedom. So I'll mention this implies rows and columns, but if we just have a single variable, we're typically just going to have columns. We'll typically just have category 1, category 2, category 3 side by side in different columns. So this technically works because we'll have one row. I guess this doesn't work because that would be 1 minus 1 is 0, and the degrees of freedom are at 0. In that particular case, if we just have one variable, we just take the number of levels of our variable minus 1. As I've mentioned before, we can do this with more than 2 variables, though this tends to be a little bit more complicated. It would still be a chi-squared, or degrees of freedom would be a little more complicated as well. We won't go too much into the chi-squared distribution, but I thought that since we're going to be using it for this, it'd be nice to have an idea of what they look like. So chi-squared distributions are not symmetrical. They tend to have a lump at the beginning and then kind of a long tail at the end. They stop at 0, which is kind of interesting. So actually, 0 isn't a number in there. So it's only defined on the positive numbers for our chi-squared. Each of these different colors represent the different degrees of freedom. And so you'll see that as you have more and more degrees of freedom, it gets more and more spread out in the positive direction. So these different degrees of freedom have an impact on the nature of the chi-square distribution that we look at. Again, these are not symmetric. So we don't have, previously we would have like a plus and minus for something like a confidence interval where we had plus and minus critical value. We're not going to be able to have that here because these are not symmetrical. Incidentally, for these tests that we're going to discuss in this lecture set, the chi-squared is we're not going to use the bottom tail. So we're just going to be looking at the top tail for our significance decisions. And ultimately what this means, because we are just looking at the top tail, is that we're going to be A, putting all of our alpha area into the top tail, and B, looking to see if our critical value is, if our test statistic is further out than the top critical value. So we're going to be looking for large positive test statistics to determine a significant difference. And recall what this distribution indicates is the distribution under the null hypothesis. So we're looking for alignment between the null hypothesis and the data, compatibility. And when we have a test statistic that's way, way over here, so it's very, very low probability that test statistic is happening, or something even more extreme than that's happening, then what we're saying is this is a very unlikely event. This data is not very compatible with this null hypothesis. And again, if I have to get rid of either the data or the null hypothesis, I'm going to get rid of the null hypothesis and keep my data because I trust my data. All right, well, this has actually been a very quick video, but I think we're going to cut it off here because in the next video, we're going to jump right into the chi-squared goodness of fit. We're going to discuss how to do it, and then we're going to jump into a couple examples, and then we'll do the chi-squared test of independence. So this is actually pretty quick. I think the background, that last video got pretty long, so hopefully this one will balance that out. But yeah, in the next video, we'll be discussing the chi-squared goodness of fit, and we're actually going to do a couple. We'll have an example I run through, an example you run through on actually performing one of these tests and interpreting it.